Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video on Math Basic Course, and as always, it is an honor and a privilege to be serving you today, as it is every day, here in my virtual classroom. Step on inside as we jump into section 2.3 in the Big Ideas Math Integrated Math 3 textbook on modeling with linear functions. I don't know why the order goes the way that it does specifically from one thing to the other. I guess it makes sense. We just came off of transforming linear functions, so there's this. But I don't know where it comes in the grand scheme of things. So just take it as it will. I'm going to go over the lecture portion and then the solution guide stuff. We'll see how it looks. Now, a lot of this is going to sound like good recap from IM1, meaning that you've done slope-intercept form. Hopefully you've done point-slope form as I see it on the screen right now. And we're going to use some of it in a stats-based way. We're going to interpret some slopes and y-intercepts and things like that. So jump on down, check this out. If you want to download the PDF in the description section, you can, and follow along with the timestamps as you see fit. If you want to check out more in the IM3 playlist, you can find that down below. So we're starting with the lecture portion here. We're going to learn to write equations of linear functions using points and slopes. Again, kind of an IM1 topic. But then a statistics topic, one you might not have done before, find lines of fit and lines of best fit. Now those are two target words, or target terms right there, core vocab. Line of fit means a line that you can make that fits your data points, and then line of best fit means a line that best fits your data points, something that a calculator can do for you unless you want to do a lot of calculations on your own. And then something called the correlation coefficient, also a stats-based thing. All those things are based on statistics. I'm going to leave correlation coefficient for when the lecture actually hits that. Previous terms here are all involved with, IM1 stuff, slope-intercept form, etc. Here's your point-slope form, and scatterplots. We saw something on scatterplots a bit ago, but our points fit perfectly through them. Now we're going to see actual scattered points. Okay. Let's write equations of a line. We know y equals mx plus b slope-intercept form. You want to use that when you're given the slope and the y-intercept in some sort of way. Either they say that, or even in a word problem if we can infer that. Given the slope and a point, you might want to use point-slope form. This is y minus y1 equals m times x minus x1. There are a lot of ways to remember what it is. If there's one as well, it's based off the slope formula, and that's what they're talking about here. Use the slope formula to find m, then use point-slope form with either given point, this one or this one, to use point-slope form and write an equation. The slope formula is y2 minus y1 over x2 minus x1. And the reason why I say this is a derivation of that is if you multiply both sides by x2 minus x1, this would say y2 minus y1 equals m times x2 minus x1. So if I erase the 2's here, then you have this, because remember x and y are variables, whereas x1 and y1 are a given point that are on your graph. So there's a way of remembering that thing if you need to use it. It's just a nice shorthand way of writing something that indicates the same exact line we're talking about without having to get it in this form, right? So two different ways. Okay, let's go ahead and take a look at an example. Writing a linear equation from a graph. The graph here shows the distance asteroid 2012 DA14 travels in x seconds. So after this number of seconds, this is how far it goes. Write an equation of the line and interpret the slope. The asteroid came within here's the second part. So here's a first part. And then a second part says the asteroid came within 17,200 miles of Earth in February 2013. Good to know. About how long does it take the asteroid to travel that distance? So that's the next question afterward, right? So our first thing is we have to figure out is we need 2 points on this graph to determine the slope. If you don't truly know where we started and where we're finishing. But we're starting from the origin. That means our y-intercept is 0. And that's what they're showing as well. B is 0. Your y-intercept here is 0. So we're starting from there, which makes sense. The asteroid hasn't traveled any time, so it hasn't traveled any distance, I suppose is the way they're saying it. And then after 5 seconds, it travels 24 miles. Pretty fast. So what is 24 divided by 5? You could leave it as that fraction, but you know what? For a lot of word problems, I say this a lot, when you're based in context, we like to use decimals when we can, especially if they're not being rounded. So 24 divided by 5 is exactly 4.8. So 4.8 is a way of saying, and we have to interpret the slope, by the way. It does travel 24 miles every 5 seconds, but that also means it travels 4.8 miles every 1 second, 4.8 miles per second. So that's where we interpret it. The slope indicates the asteroid travels 4.8 miles per second. And then use the equation to find how long it takes the asteroid to travel 17,200 miles. So y is the number of miles traveled, x is the amount of time taken. So if you set y equal to 17,200 and divide both sides by 4.8, you get approximately 3,583 seconds, 3,600 seconds. So it's about an hour. about an hour, according to that one. Okay, let's move forward. Example 2 in modeling with mathematics. 2 prom venues charge a rental fee plus a fee per student. The table shows the total cost for different numbers of students at Lakeside Inn. The total cost y in dollars for X students at Sunview Resort is represented by the equation here. So we have Lakeside Inn table modeling how much was spent over time, or the cost based on number of students, and we have an equation of this one. Which venue charges less per student? How many students must attend for the total cost to be the same? So that's 2 different questions, right? Once again, first question I'll put in green. Which venue charges less per student? We're looking for rates. Now this one is in slope-intercept form, so they're giving you the rate right now. It costs $10 per student. There's an upfront cost, right? Rental fee. There's an upfront cost, but then there's a fee per student there. What's this cost per student? We have to do a slope. We have to take any 2 points, find the difference between the y's and the difference between the x's, and divide them. So if I were to do it, I'm looking at like the difference between 1,500 and 1,800 is 300. You do 1,800 minus 1,500. The difference between 100 and 125 is 25. So after 25 students and change, there are $300 in difference. So what is $300 divided by 25 students is the question. And then you do that division. So I'm assuming they're going to do the same. Let's take a look. Here it is. They're y2 minus y1 over x2 minus x1. 1,800 minus 1,500 over 125 minus 100. 300 over 25 is 12. That means they are charging $12 per student at Lakeside Inn. So which venue charges less per student? Sunview Resort charges less per student. This is just that part A, if you will. Now, they're doing a whole equation afterward. I'm just trying to answer that one question first. So it looks like I'm trying to figure out where they actually answer that first part. Looks like they do it way down here. So comparing the slopes of the equations, Sunview Resort charges $10 per student, which is less than $12 per student Lakeside Inn charges. That's the first part. The second question is, when are the costs the same? This is where you want to make this an equation out of this one, because we want to figure out when does this y, for what x does this y equal the same y given that x? So we want to figure out, we want to set these equations equal to each other. We want to put this one in slope-intercept form. So we started to do that sort of, right? We got the slope of this thing. We found out that the slope is 12. So we have an equation that would, you have 2 different ways. They're going to stay on point slope form. I suppose I will as well. That's fine. I have no problem with it. You can do either slope-intercept or point slope. But they're going to plug in a point, and they plugged in the smallest point. This is the second question, by the way. How many students must attend? Let me use my cursor. How many students must attend for the total cost to be the same? So here we found the slope again of 12. They're going to choose this point right here of 100 students and 1,500 cost. So x and y, substitute those for y1 and x1. And they're going to rewrite this thing in slope-intercept form. They're going to distribute the 12 and add the 1,500 over. So we have an equation for basically the rental fee of Lakeside Inn and the cost per student. And then we're going to set these y's equal to each other. When does the y from the, what is it called? Sunview Resort equal the cost for Lakeside Inn? How many students? After how many students is the cost the same? So we solve for x, we get 150. So after 150 students, the total costs are the same. Before that, you're probably paying less at Sunset Resort or whatever it's called. And then, at Lakeside Inn. And then afterward, you're paying less at Sunview Resort. Okay. Now the cost would have been $2,100 for each of them if they asked that. Okay, finding lines of fit and lines of best fit. Data do not always show an exact linear relationship, meaning an exact point, rise, run, you get this point, rise, run. Not all points are always on the line for all data. When the data in a scatter plot show an approximately linear relationship, you can model the data with a line of fit. So creating a line of fit means, step 1, create a scatter plot of the data. So just to show you an example, they're showing you a table of values here. We're going to go back to this. But this table of values, if you plot the points, you can see they're not exactly in a perfect line. Anyway, so create a scatter plot of the data would be doing that, finding all the points and adding them. Sketch a line that most closely appears to follow the trend given by the data points. There should be about as many points above the line as below it. So this line was estimated and drawn afterward. This is something you're just going to have to eyeball, and I'll be doing the same thing. I'm just going to eyeball it. Your line may not be the same as mine when it's drawn. Mine might be better, mine might be worse. Or maybe we have our own versions of what's still okay. Choose 2 points on the line and estimate the coordinates of each point. These 2 points do not have to be original data points. So here's the thing, right? When I draw a line that goes through here, maybe the line doesn't strike through exact data points. So I want to find values that I know I can actually hit. When it's based on scale, and they're kind of showing you 2 points that they're working off of. When I go based off scale, I want to find things that I think make most sense. They chose apparently 40, 170 and 50, 195. We'll talk about those. But from those, you can come up with step 4, write an equation of the line. You can do an equation based off the slope and the y-intercept of what you believe are points on the line that you drew. So again, they don't have to be original data points, but if your line seems to go through an original data point, I guess use it. But don't try and draw your line so that it goes through the data points. Try and draw a line of fit, the line that seems to work that one best. So let's go through this whole example now that I spoke on all that. The table shows the femur lengths in centimeters and heights in centimeters of several people. So here are the centimeters of people's femur lengths and their corresponding heights in centimeters. I don't know how centimeters work for measuring people. I'm an inches person, of course, or feet. Do the data show a linear relationship? If so, write an equation of a line of fit and use it to estimate the height of a person whose femur is 35 centimeters long. So you can often use your line of fit to then interpolate or extrapolate what your data is based off your line, meaning come up with predictions of values for actual data points you don't have to predict something. That's a good reason to do it if your line of fit seems to be a valid one. And this one does seem to be. When they plotted all these points here, which is going to be us doing it quite a bit, when they plotted all the points here, it seems like there's a good line that goes through there, and it does seem to fit the data pretty well. So they sketched their own line. I'm not going to do it based off theirs, and theirs is a very small window, very small scale, so it's hard for me to do something on top of it. But they chose 2 points that were on this line, 4170 and 5195. From there, they found the slope. They chose those to divide the rise over run, and they got 2.5. And then they used point slope form with a given point that was on their line, either 4170 or 5195. When in doubt, go for the smaller numbers or the ones that multiply best. And then they got a y-intercept for themselves. Now, the y-intercept is a true extrapolation of your data, and it's kind of a weird number as well, because if you interpret the y-intercept, and not that we're doing it here, but to interpret the y-intercept, what that means to us is a person with 0 centimeter femur length would still have a height of a person with 0 centimeter femur length would still have a height of 70 centimeters. And I don't know how that thing works. At some point, your data doesn't really seem to work in your model. But it seems to work for the information we have here, and we want to find it at a person who is 35 centimeters in height. So based off their line there, it's going to be somewhere close to 160 centimeters, but we're, of course, going to substitute 35 into our equation that we made. So we're going to do 2.5 times 35 plus 70, which is 157.5 centimeters. The approximate height of a person with a 35, whoops, you can't see that, with a 35 centimeter femur is 157.5 centimeters. Now, that's our interpolation of that information. Interpolation, whenever I say that phrase interpolation, I mean predicting data from our model that fits between our points that we have. An extrapolation would be predicting data outside of our model, like something out here, right? Our data points fit within this domain, but outside of it, this prediction would be considered an extrapolation. That's something that we can't guarantee would really work within that realm, just like I said, a person with 0 centimeter femur, or a person with a 600 centimeter femur, right? Who knows how it's going to work when you get that big, because we just don't have any data that shows that. Anyway, let's talk about the line of best fit. We drew a line of fit the best we could eyeball. The line of best fit can actually be calculated. Our calculator can do it, and that's probably the best way we're going to do it. Line of best fit is a line that lies as close as possible to all the data points. Many technology tools have a linear regression feature you can use to find the line, such as graphing calculators. My graphing calculator does the same. The correlation coefficient, denoted by r, that means that's our variable for it, is a number from -1 to 1 that measures how well a line fits the data set of data pairs x, y. When r is near 1, the points lie close to a line with a positive slope. When r is near -1, the points lie close to a line with a negative slope. When r is near 0, the points do not lie any close to any line. So what they're saying here is you're going to get some r value, and I'm going to give you an example. I'm going to show you the example down here. They're going to give you some r value, and for the most part, it's going to be a decimal, right? Unless your points are exactly going through a perfect line, you're going to have some sort of strange decimal. It's going to look like that. Okay. Now, the idea is there's a trend for R, and I don't know if they have a table. Let me kind of skip forward. Oh, good. We have the problem set after. So let me kind of like make a table for you guys and talk about how R basically works and how you can interpret it. R ranges from, as they said, -1 to +1. So here's -1, here's 1, and here's 0 in between. And then, you know, there are some points of ranges. You can have like 0.5 and 0.75 and 0.25, -0.25, -0.5, -0.75, like that. The closer you trend to -1 or +1, the stronger your correlation is. These ones over here have a very strong correlation. You might have heard the word correlation before. Correlation just means the way that you can relate two things, like as one goes up, the other goes up, or as one goes up, the other goes down, or something like that. And 0, the closer you get to 0, the weaker your correlation is. Literally, if you had 0, there would be 0 correlation, meaning there's no relationship between these two things that you can link. So the closer it gets to 1, the stronger the correlation is. Now, there are certain decimals where you can interpret and say that's a very strong correlation, as opposed to there's a moderate correlation, or there's some correlation, or there's weak correlation. You get around 0.25 or something, guys. That's a pretty weak correlation. 0.5 is very moderate. Very, very much some. There may be some correlation, but not much. You're starting to see a correlation around 0.75, and the closer you get to like 0.9 or so, it's starting to look very strong. 0.95, very strong. 0.99, something like that. You're looking like, yep, these have some sort of link. Now, when it gets negative, that doesn't make it bad. That just means it's from a negative slope. That means as something goes up, as x goes positive, y goes negative. So a correlation of -1 and a correlation of 1 are both perfect correlations. They're both perfect correlations. 1 is for a positive perfect correlation. -1's for a perfect negative correlation. Now, they don't say it here, but correlation doesn't mean causation. That's an important phrase that we say. I'm going to type that. Correlation does not necessarily mean causation. In other words, just because two things relate to each other doesn't mean one causes the other to happen. There can be a lot of other links in the chain that allow another thing of correlation or other things to explain why that case is what it is. So correlation doesn't necessarily mean causation. I don't know if that matters out of this stuff because they haven't talked about it. I don't know if we have to interpret this stuff either. Now, the only other thing I want to state here is that the R value itself is just for us to state how strong the correlation is. The number itself doesn't mean anything. R squared, however, is a number that means something. And I doubt we're going to talk about R squared, but let's say, because R squared is 0.989, that means R squared is about 0.99, right? R squared can be represented as a percentage as well. R squared, it does literally mean squaring R, but R squared actually has meaning to the number. It actually means, if I said 0.99, it would mean, it would mean 99% of your data can be explained by the link between these two things, and the other 1% could be explained by something else. The 0.9945, etc., is not a number that actually means anything. It just indicates strength of correlation. Anyway. Okay. Excuse me. I have some sniffle issues. Okay. Let's look at how they use the graphing calculator for this. And I'm not going to type them out in this one, but thankfully I use the same kind of graphing calculator that they're going to use that has this window appearance and such. So hopefully you have a TI-83 or some sort of Texas Instruments graphing calculator. You can follow along with me perfectly. If not, you're going to have to find the certain features and tools for you. Use the linear regression feature on a graphing calculator to find an equation of the line of best fit. So they're going to input all their values into here. Now, to show you where that information is, although I'm not going to type it, show you where that information is on the graphing calculator, you go to Stat, right here, and you go to Edit. So you can start entering some data into L1 and L2. You would treat L1 as your X variable and L2 as your Y variable in this case. And then they say, enter the data into the two lists, and then use the linear regression feature. Now for us in the calculator, the linear regression feature will be, let's see, that's the second button. Vars? Where is it? Why var? Let's see. Distribution list. I can't remember where it is suddenly. Let me think about it. Stat. Oh, maybe it's still in stat. Oh, stat calc. There it is. Stat calc, and we'll use linear regression AX plus B. AX plus B is the same thing to us as MX plus B, right? A is the slope, B is the y-intercept, that kind of thing. So when they have that information spit out, you can tell, whoopsie, you can tell that they have, sorry if that showed up on the previous slide as well. They have several pieces here. A is your slope. Your y-intercept here is B. Now you can tell that that's rounding to about 65. This number is around 2.6, and we're going to have to do some form of rounding for this, unfortunately. So y equals 2.6x plus 6.5 is the number they're going to use, or the slope. What did they have before? 2.5x plus 70. Close, but this was line of fit, not line of best fit. This is a line of best fit. Your calculator is doing a lot of under the hood calculations to make this happen, and it's making the correlation as strong as possible. That's its aim, to make an equation whose correlation is as strong as possible. Basically, the line is best fitting within the points in that distance. They graph it as well. You'd have to then type that equation in. I don't think there's a way to just copy paste that thing. So you would actually have to go to y equals and type your 2.6x, like that kind of thing there. And then, let me clear that out. And then from there, you have your points on a scatter plot as well. I do believe, let me make sure everything else is on for me, or I'll show you how to do the rest based off this. Yeah, I just have to make sure that I'm able to plot my points. I'll check and find out how to do that later. Oh, stat plot, that's how you do it. Okay, I'll be ready to do all of this for you guys when the time comes. I guess your teacher would have to talk to you about how that stuff works as well. Sorry, I'm playing with the calculator features. Okay. So the approximate height, this is why they're doing this. Because when they draw this thing, they need to then trace and find out when x is 35, what y value do you get. So when x is 35 for this equation, it's going to trace a value of 156. Now you could plug it into your equation, that's fine. But your calculator can also do it for you. So you get 156 centimeters compared to the 157.5 that we interpolated. So that's fine. Okay. And anyway, that'll end the lecture portion as we jump now into the problem set, starting with the vocabulary and core concept check. Complete the sentence. The linear equation y equals 1/2 x plus 3 is written in, that's called slope-intercept form. I'll just write slope-int to fit that. Your slope is 1/2, your y-intercept is 3. Point slope form has kind of something with y on its side, and slope is multiplied by a difference on the x things. You've seen that before. A line of best fit has a correlation coefficient of -0.98. What can you conclude about the slope of the line? So, well, first of all, regarding the correlation, what I can conclude is it's a pretty strong correlation. Now, the correlation is also negative, which also means your slope is negative. The slope of the line is negative whenever the correlation is negative. That just means there's a downward trend from your line that is best fitting your points. Okay, guys, I'm going to go ahead and get started with the problem set. It is numbers 3 through, I think, 32. So let's go ahead and take a look at those together. We'll see how often we have to use the calculator versus do our own thing. It's getting things set. Ready, steady, go. I wasn't really prepared, apparently. Okay. Oh, you know what? Give me 1 second. Let me build my circle. I totally wasn't prepared because I don't think I built my circle on any of these. Let me pause this. Okay. Ta-da. Okay, in exercises 3 through 8, use the graph to write an equation of the line and interpret the slope. So on number 3, and I'm going to keep the graph over on that side, but on number 3, we have a point that's 10, 2, that's 10 on x, 2 on y. That's a rise of 2 and a run of 10, though, from 0, 0. You have to remember that that's your origin. So on number 3, you do have a y-intercept of 0, which I'm going to go and use slope-intercept form for that. Your slope is going to be your change in y over change in x. We're rising 2, and we're running 10. Now that reduces to 1/5, and I'll go and leave it as a fraction. Unless it's contextual, I'm going to leave it like that. So the equation should be y equals 1/5 x plus 0, or better written as just y equals 1/5 x. Not necessarily better written, but if they ever write it that way, you have to know that that means the y-intercept is 0 on that problem. So there's number 3, looks to be pretty fast. Oh, interpret the slope. I take it back. This is context-based. Let's actually turn it into 0.2. I forgot this is contextual. Okay, so 1 divided by 5 is 0.2. Now, this is about the cost of meal in dollars and the amount that you tip. Aha, in dollars. So the interpretation is that rise and run. You can either do it in fraction form or decimal form. So let me say either or on this one and see which one kind of sounds best. You tip $1. This is the fraction version. You tip $1 for every $5 spent in a meal, in the cost of a meal. That one actually sounds pretty good. Or for every dollar spent in the cost of a meal, you tip 20 cents, right? $0.2 is 20 cents. So for every dollar spent, you tip an additional 20 cents with that. So yeah, either or can be written depending on which way you want to actually write that. I think they both work pretty well. Basically, your tip, I mean, this is a customary thing. Whether you choose to do that or not, it's up to you. But, oh no, I was trying to get rid of the bullet points because it seemed to screw things up. But basically, 20% tip. Pretty customary. Somewhere between 15 is a little lowballing these days. 18%, 20%, something like that. Get generous, do 25%. Round out to your nearest dollar, up to you. But I tend to do around 20% myself. Okay, number 4. Remind me to keep interpreting slope. This is regarding gasoline tank. The amount you travel. And by the way, this, I won't call it positive correlation, but that's a positive slope. Here's an example of a negative slope. Negative slope doesn't always mean a bad thing, but anyway. How far you travel versus the amount of fuel that you have left in your tank. Not how much fuel is consumed, but the amount that's left. First of all, let's attack the y-intercept. The y-intercept appears to be 2, 4, 6, 8, 10, 12. So our b value is 12. And the slope is the change in y over change in x. Now the original point that we have there, that is 0, 12. Oh, you know what? I take it back. They show you a slope right there. They show you a run of 90 and a fall of 3. Now that fall means negative. We're going down 3 every time we go over 90, which is negative 1/30th. I think this time I'm going to leave it as a fraction because otherwise this would be a strange repeated decimal. So I'm going to write this equation as y equals negative 1/30th x plus 12. Now I'm going to interpret a couple things for you. I will interpret slope, but let's first talk y-intercept on this one. First of all, on the meal one, you spend $0 a meal, you're not going to tip anything. That makes sense. Here, if you don't travel any distance, you're going to be at max fuel of 12 gallons. That's what the 12 represents. What does your slope represent, though? It represents for every 90 miles traveled, you consume 3 gallons of fuel, or you lose 3 gallons of fuel. For every, I'm going to make this bigger. For every 90 miles traveled, you consume for every 30. For every 30 miles traveled, you lose 1 gallon of fuel. Right? That's where we have the slope that's actually like reduced fraction. Do the actual reduced one that you have. Okay, number 5. Savings account. How much time in weeks has elapsed, and what your balance is in dollars. Whether it's gaining interest, whether you're adding to it, whether it's making money, whatever, like that. Okay, so let's go to the y-intercept. Now, there's a break right here. You're like, what the heck is that thing? That shows that this isn't going down to 0 right here. That means this isn't going 75, 150, etc. There's a break in that action. We have to see the difference between here and here. Looks like it's going every 50. So if it's going down 50 right here, that means this would be 100, and that's going to be our y-intercept for this one. So I'm going to go ahead and use that point right there. If I can use y-intercept, I will. So in this case, the y-intercept is 100, and the slope is our rise over run of this thing. We're rising 100, and we're running 2. Now, they did give us a point on the graph as well. I'm not intent on actually using point slope form if I don't have to. I'm going to use slope-intercept form as often as I can. So 100 over 2 is 50. Remember, that does mean 50 over 1. That's important when we start to interpret slope. But y equals 50x plus 100. Now, my full interpretation of this is going to be the 100 means with 0 time in weeks, I had $100 in my savings account already. Just when I opened up my savings account, I probably had 100 to start. Just put it down. The 50 is also 50 over 1. That means every 1 week, right? The 50 over 1 is every week there's an additional $50 added or deposited or whatever. I don't know if we're earning it or how it's working. I guess we're adding. Every 1 week, another $50 is added to the savings account. Okay, 50 is 50 over 1. It's the reduced fraction of that. Okay, number 6. Tree growth, or the height of the tree in years. So we once again have a y-intercept of 0, and you have a slope with a rise of 6 and a run of 4. Change in y over change in x, which reduces to 3 over 2. You could also say 1.5. Yeah, let's use the 1.5 this time. Y equals 1.5x would be the equation, considering that 0 is the y-intercept, because at 0 years old, the tree has 0 height, apparently. Makes sense. It's not yet grown. So interpreting the slope here would be every year, the tree grows another 1.5 feet. Okay. All right, numbers 7 and 8. Ooh, typing speed and time. All right. How much words typed in a certain amount of time. Now, this is literally going to be a rate. This is how many words you can type per minute. So I'm definitely going to be doing one of those things here. Now, this one, I think that, I guess it makes sense. That's at 0, 0. It looks like they really want to push you to use point slope form here and there. As long as I can see my y-intercept, though, I'm going to be using it. So I see a y-intercept of 0, which makes sense. No time, no words can be typed. But the slope, we now have to compute ourselves. We're going to do a rise over run comparison. How much do you rise from 55 to 165? That is our 165 minus 55 change in y. How much do we run from 1 to 3? That is our change in x. So we're going up a certain amount over a certain amount. Now, you don't have to calculate this if you truly know your numbers, meaning what's the difference between 1 and 3? You know that that's 2. But if you want the formula, here's where it is. And that changes 110 words every 2 minutes, which is 55 words per minute, right? That is interpreting the slope, by the way. We're already there. Now, the equation is y equals 55x plus 0, a directly proportional relationship, which states every minute you type 55 words, you type 55 words per minute. I mean, I literally want to get into that WPM kind of thing. Now, I tend to type more. I know I screw up my typing here a lot. It's for a lot of different reasons. I'm reaching beyond a microphone and things like that. But I'm just going to leave it there. Okay, number 8. Swimming pool. Time and volume. Volume. I guess this pool's draining. You're losing poolage. This y-intercept, I don't know for sure. I'm not going to guess it. I don't know it. So I'm not going to use slope-intercept form. I do not see what this y-intercept is. But I do have 2 points. So this is one that is very, very built for point slope form. Recalling point slope form is y minus y1 equals m times x minus x1. There's nothing inherently bad about this. You just got to know what it looks like. We can rewrite this in slope-intercept form if we truly wanted to. And I will for your sake, just so you know what it is. But we do have 2 data points we have to begin with to find that slope. Same way as we found slope before. M is... we can do you can choose how you want to do this. I'm going to do 180 minus 300. I'm going to have the negative number on top over 5 minus 3. So 5 minus 3 is 2. 180 minus 300 is negative 120, which this reduces to negative 60 or negative 60 over 1. Now, when it comes to point slope form, you can choose either set of points to build off of, like say this one. This is going to be an x1, y1. So I can make this say y minus 300 equals m times x minus x1, which would be 3. That's an equation that you can write. Or you can choose the other set of points. Maybe you didn't choose that set. You're like, wait a minute, Mr. Robinson, I chose the other one. Okay, we could have chosen y minus 180. Y minus 180 equals negative 60, still the same slope, times x minus 5. See, the reason people don't like point slope form, among other things, is when there's more than one answer, they're like, wait, how can you have more than one line? This isn't more than one line. They're both the same line. If you want me to verify that, let's take either of these and let's rewrite it in slope-intercept form. Let's see what that actual y-intercept is. I'm going to guess 300, 400, 500. I'm going to guess it's around 480. So let's see what it actually will be. Let's take the first equation right here. Let's distribute negative 60. Negative 60x plus, because negative times plus 180, and then, yeah, you add 300, you get negative 60x plus 480. So I guess I was right with that number. I didn't plan on being right. But we should get the same answer of this one right here if we distribute the negative 60 into there. We get y minus 180 equals negative 60x plus 300, and you add 180 over, you get y equals negative 60x plus 480. So the fact of the matter is you get the same thing. So, or you can write this equation as well, but that would come off of point slope form, or even if you don't use point slope form to get it, you still can't eyeball this number. I was right, but you can't do that as a general thing. These other ones weren't eyeballed. These other ones were exactly at the origin or exactly at the crosshairs of this thing. These ones, however, were. So we have three different sets of the equation, 1, 2, or 3. Any of those are valid. We still have to interpret the slope, which is saying how many gallons, how many cubic feet of pool water is being lost per hour, which is, I guess it's draining. The pool is draining 60 cubic feet of water every hour, or losing, or whatever you want to say. All right, that's numbers 3 through 8. Let's keep moving forward. Number 9, modeling with mathematics. 2 newspapers charge a fee for placing an advertisement in their paper, plus a fee based on the number of lines in the advertisement. So the fee for placing an advertisement is like an initial amount, kind of like a y-intercept. So like your B, if you will. The fee based on the number of lines, that's kind of a slope. How many dollars per line? The table shows the total cost for different length advertisements at the Daily Times. The total cost y in dollars for an advertisement that is X lines long at the Greenville Journal is represented by the equation here. So we have one with a table and one that's written out as a model already. So for Greenville, I'll call that y sub g, and that's going to be 2x plus 20. We don't generally have to do the y sub g kind of stuff, but I'm going to do it at least to start with here. Which newspaper charges less per line? That's kind of a part A. How many lines must be in an advertisement for total cost to be the same? That's a part B. So which charges less per line? You know, this slope means that Greenville charges $2 per line. How much does the other charge per line? We have to find the slope based on the table. So based on the table, I can see that every time you increase one line, you are adding an extra $3. So that's going to be a slope. That's a rise of 3 and a run of 1. So for the slope for the Daily Times, I'll just put D. The slope for Daily Times, that's going to be 3 over 1, which is $3 per line. So regarding part A, which one charges less per line? The Greenville Times. The Greenville Journal, excuse me. The Greenville Journal charges less per line. $2 versus $3. Now, part B is when will these costs be the same? We still have to, for the Daily Journal, or whatever you call it, the Daily Times, we still have to come up with its equation, this whole y minus y1 kind of thing. So I'll call it y sub d. Y sub d minus, and let's choose a point on this thing. Let's choose 4 and 27. Fine. Minus 27 equals our slope m times x minus 4. So that's y sub d minus 27 equals 3x minus 12. And then we'll add 27 over. I'm basically getting the slope-intercept form version of this. 3x plus 15, I think. 27 is 15. So we have an equation here of 2x plus 20, another equation of 3x plus 15. We have to set these two equal to each other. So when does the y for the Daily Times equal the y for the Greenville Journal? When does y sub d equal y sub g? That's where we set 3x plus 15 equal to 2x plus 20. So I probably overwrote and overworked using this whole subscript thing. Next time I won't do that. We'll just have to follow along with which one represents what. But now we solve for x. We subtract 2x from both sides, subtract 5 from both sides. X equals 5, which is a way of stating what? After 5 lines, you spend the same amount. Both newspapers charge the same amount after 5 lines of advertising. See, there's an upfront cost. The upfront cost is $15 to place the ad, $20 to place the ad, $3 per line, $2 per line. Eventually, they both spend, by the way, they both spend $30 for that. spending 30. You can tell in the table. At 5, you spend 30. If you plug in 5 here, you also get 30. Okay, that's number 9. Number 10. Problem solving. While on vacation in Canada, you notice that temperatures are reported in degrees Celsius. Yep. You know there's a linear relationship between Fahrenheit and Celsius, but you forget the formula. I think I know it. From science class, you remember the freezing point of water, 0 degrees Celsius or 32 degrees Fahrenheit, and its boiling point is 100 degrees Celsius or 212 degrees Fahrenheit. That's the one I didn't remember. I knew it was something. I thought it could have been that, but let's come up with the formula together. Write an equation that represents degrees Fahrenheit in terms of degrees Celsius. So in terms of means we want F equals and then something with C. F equals blank C plus blank, basically, is the way we're doing that. Okay? So this is for number 10. What we have is information for a slope and information for a y-intercept. Information for a slope, and then we can use that to get, information to create an equation based off slope. So we have one set of points, which is 0 degrees Celsius or 32 degrees Fahrenheit. We have another bit of information that is 100 degrees Celsius or 212 degrees Fahrenheit. So we can take that change in terms of rise and run and stuff. And I assume we need that as our x and y, right? If this is our x and this is our y, then we want Celsius to be x and Fahrenheit to be y. So looks like we're in the right mindset for rise and run. So what is our slope? We're going to rise from 32 to 212, and we're going to run from 0 to 100. So we get here 180 over 100, which does reduce to 9/5. And I'm going to leave it as 9/5. I believe whenever we write this as a fraction, in reality, we tend to do that instead of 1.8, although you could also write 1.8. But I'm going to leave this one as 9/5. So with that, we also have a y-intercept. Our b value in this case is also 32 because this is the value of y when x equals 0. So m is 9/5, b is 32. We can have an equation that's y equals 9/5 x plus 32, or f equals 9/5 c. F equals 9/5 c plus 32. This is your formula for converting Celsius to Fahrenheit. You can also convert Fahrenheit to Celsius if you do some of the work. The temperature outside is 22 degrees Celsius. What is this temperature in degrees Fahrenheit? This is now where you do a substitution. Oh, that was part A, by the way. Part A. Part B, F is 9/5 of 22 plus 32. I'll probably go to the calculator for this. It looks like it's going to be some sort of decimal. 9/5 of 22 plus 32 is going to be 71.6. So exactly 71.6 degrees. It's Fahrenheit. I know that's weird to show the F and the F here, but I'm just going to say it like that. 71.6 degrees Fahrenheit outside. Pretty good temp. Ideal. Rewrite your equation in part A to represent degrees Celsius in terms of degrees Fahrenheit. This is the other one I was talking about. So now what we're going to do is solve for C in this equation. So we have the equation F equals 9/5 C plus 32. Let's get C by itself by doing two things. We're going to subtract 32 from both sides. And then we're going to divide both sides by 9/5. That also means multiply both sides by 5/9, which means a 5 goes on top. Now, when I do it on this side, I have to multiply this quantity by that, which means this will be wrapped in parentheses. So the way that this should be written best ultimately is C equals 5/9 times F minus 32 in parentheses. So there are, this is what's called, you did this probably in IM2 as well. This is what's called, finding an inverse. Taking that inverse and kind of doing that, or at least solving in terms of the other equation. You inverted everything. Part D, the temperature of the hotel pool water is 83 degrees Fahrenheit. What is the temperature in degrees Celsius? This time we will substitute 83 for F. So C, part D, C equals 5/9 times 83 minus 32. That's 5/9 of 51. Also let the calculator work this one out. Looks like there's going to be a little bit of rounding. 5/9 times 51. I'm getting 28.3 degrees about. 28.3 degrees Celsius. So for myself, I'm kind of when it comes to degrees Celsius. I can't really see the number and know what it means. Obviously 0 and 100 I do, but anything else, I can't tell if that's hot or cold. 83, I'm saying, it's pretty good. Pretty good pool water. Temp. All right. Okay, numbers 11 and 12 are error analysis. Let's go. In exercise 11 and 12, describe and correct the error in interpreting the slope in the context of the situation. Maybe they'll do a run versus rise or something. Run over rise instead of rise over run. The slope of the line is 10, so after 7 years, the balance is $70. That's not interpreting a slope there, but is the slope of the line 10? You go from 0 to 4, which is 4. You go from, so the slope is 10. I don't know what this has to do with slope. They might be right. After 7 years, the balance is, well, it's not $70 either. I don't know what that has to do with interpreting slope anyway. They never interpreted slope, and whatever they mentioned is wrong. Oh, I see what they're saying. They never interpreted... Okay, hold on. Their interpretation of slope made no assumption about the initial balance or the y-intercept. See, here's the thing. What they're saying is after 7 years, $70 will be accumulated. That is a true interpretation of that slope. 70 over 7 is also 10. But there's a y-intercept that takes hold, right? You may add $70 after 7 years, but how much did you start with? We started with $100. So we should actually have $170 at that point. Now, that's not an interpretation of the slope regardless. But after 7 years, they will have added $70, but they are adding it to the $100 they initially had, which is now $170 total. Now, that's still not a slope interpretation. I think the best slope interpretation is using that 10. Correction. So the correction should be after 1 year, or every year, your balance increases by $10. $10 per year. That's the correct. That's the correct slope interpretation we're gonna work off of. So I don't really know where they were going with their stuff. I do, but I don't. They weren't even interpreting slope to begin with, and it was a wrong value with it. All right, let's go to number 12. The slope is 3, so the income is $3 per hour. That would be a correct, if the slope was 3, that would be a correct interpretation. But that slope appears to be incorrect on number 12. They look to rise 33 as they run 3. A rise of 33 divided by a run of 3 is going to be a different value other than 3. Although their interpretation of their slope is on point, they have the incorrect slope. So let's correct their slope, and then let's write it exactly as they wrote it for the other part. So the slope should be change in y over change in x, 33 over 3, which is 11. So how do we interpret that one? We say the income is $11 per hour. $3 per hour is a poor income. The income, not the slope. The income is $11 per hour. Okay, there we go. Okay, numbers 13 to 16. Determine whether the data show a linear relationship. If so, write an equation of a line of fit, estimate y when x equals 15, and explain its meaning in the context of the situation. Now, this is where I'm going to struggle a little bit when it comes to scale. I guess I will try and use my graph. Maybe I'll use the long one here and see if it works best for what I have, or the tall one, I should say. I wonder if I should do it this way or that way for my numbers. I guess I'll just go this way. I don't know. I want something to be to scale. Otherwise, it's just going to look a little wonky. I don't think I'll get very good lines of fit. I'll attach this graph paper onto my stuff here. So sorry if this gets a little strange. I'm going to leave the table values as they are, and we'll plot some things. But it looks like here, my x, oh, that's x over here. My x, this will be tricky for me to determine how I want to do some of these. Let's see. I want to use I'm going to use the other stuff to keep it squared away so I don't have to think every time on them which one I want to use. So I'm going to use this one instead. Now, I only am going to use the first quadrant anyway. So, but I want to change scales on these things. X, I'll go by 2s. Y, I'll go by 10s. So this will be 50 and 100. So this is calories burned. And this is minutes walking. Okay, we got to plot these points. They say line of fit, not line of best fit. So we're going to do this all on our own, eyeballing it. After 1 minute, 6 calories are burned. One is, here's 2, so 1 is right here. 6 is a little more than half of 10, like that, because these are going by 10s. So there's one of my points on my graph. So you can see it's going to be kind of when we do these. 6, 2, 4, 6, and 27, 10, 20, 27 is there. 11 and 50. Here's 11. Here's 50. That one is probably one of my best eyeballing ones I can do. 13 and 56. Here's 12, 13, and 56. This looks pretty linear. Glad we started with a linear one. 16 and 70. 12, 14, 16. Oh, 70 is going to be the perfect one. All right, I can get that one. Okay, so does it form a linear relationship? Yes. So determine whether it does. Yes, linear. Yay. If so, write an equation of a line of fit. Estimate y when x equals 15 and explain its meaning in the context of the situation. So my line of fit that I want to draw, and I really want to thin it out, I want to draw something that best appears like it's going through these points in some sort of way. Kind of like this, right? I'm not going to be perfect on any of these, but this is the idea. Draw a line that seems to best go through your points. And I'd say that's a pretty decent one right there. Wouldn't you agree? Not bad. Okay. So there's my line of best fit. Now we have to come up with an equation for this line. So in order to do that, you can do a couple things. You can come up with 2 points that you think this line crosses best. Sometimes I try to look for the crosshair bits, and it doesn't look like it really does. It probably hits through that point that I have pretty well and this point pretty well. So I'll go ahead and just choose those 2 points. This is just me roughing it. I did not intend to do that, but I'll go ahead and use them. If I use the point here that was, actually, you know what? It seems to even kind of go through this point pretty well. So let's use this one. That's 2, 10, 2, 10. And then this one here is that same point that we had on the graph, which is 1670. So let's just make it off that. Your line might be different than mine and whatever. Your equation might be different. That's why I want that line to be very thin. So my equation, and this is just for room's sake, I'm going to write it right here. This is, my slope is going to be rise of 60 over run of 14. Now, 60 over 14 is not a clean number. I almost now want to change it. It's 30 over 7. So let's see. I'll keep it as 30 over 7 for now because they never have us interpret slope. So I'm going to leave it exact. But they say write an equation of a line of fit and estimate y when x equals 15. So now I have y minus y1, I'll choose 10, equals m times x minus x1, x minus 2. The problem with this one is now we're going to have just some fraction stuff, and there's nothing I can really do about that unless I do rounding. And I don't know if rounding is the ideal way to do this, but I'm going to distribute this, and then I'm going to add 10 to both sides. Now 10 is also 70 over 7. So negative 60 over 7 plus 70 over 7 is 10 over 7. So here's my line of best fit without any rounding done. Now I'm going to round ultimately. They say estimate y when x equals 15. So when x equals 15, we have to do this 4 times. This is going to be pretty long. So we're going to say y equals 30/7 times 15 plus 10/7. And I'm going to use the calculator to approximate this one. I'm not going to keep it as a fraction anymore. So I just didn't want to round it early. 30/7 times 15 plus 10/7. For me, my chosen points is 65.7 about. Y is about 65.7. Now, what was the context of this? Calories burned and stuff? Calories burned, minutes walking. So 65.7 says after 15 minutes, you will burn about approximately 65.7 calories. After walking 15 minutes, you will burn approximately 65.7 calories. So that's the interpretation of that part. Looks like I didn't have to interpret slope, so I'm good there. Okay, number 14. Yeah, so we have a lot to do on these ones. Like I said, I'll use my scaled graph stuff to work it out. Now, I do wonder, they said determine whether it's linear or not. I do wonder if we'll have some that are not linear. And if they aren't, do we have to do anything after that? I'm guessing not, unless we're going to draw a curve of fit. And I highly doubt we're going to do that. All right, number of months goes to 23. Should I go by threes? Hair length. All right, I'm going to go by ones here. I think that's fine. I'm just going to go by twos here. 23 goes a little bit off, but I'll be best in my approximation as I can. So 9 for X, 3 for Y. So 9 is here, and then 1, 2, 3. 13, oh, a couple of these will go off. 12, 13, comma 5. 18 is right here, comma 7. 22, okay, I'll say that's like 22 and 24. Whoops, that's a little more spaced. 22, 24. All right, 22, comma 10. That's pretty close. And 23, basically where the X is. 23, comma 11. So 11 is going to be about right up there. So a little bit off the graph. Doing what I can. That's pretty linear, right? All these are pretty strong in correlation. So this one's going to, that's not a very good line just yet. I'm just roughing it out. You can kind of use a ruler when you do these and go through like, yeah, that's going to work out. You want about as many, as they said, about as many below as you do above, or the strength of the thing needs to go like that. So there's my line of fit that I'm working off of. Okay, I'm just going to work off that. And I can't guarantee it's going through any one of these points. Let's find kind of crosshair points it's going through. That's what I'm looking for. Let me extend this farther just to be sure that I'm kind of getting any set of points. Remember, you can choose any 2 points that you feel like it's going through decently. So for me, I'm going to choose, so this one, even though it's negative, it has nothing to do with my model, but it seems like a set of points that it's going through. And, it's kind of going through that one. Okay, so I'm just going to use that one, even though that was a rough one. So that point is 22, comma 10. And then I have this point way down here. It's a negative one. It's kind of weird. But negative 4, remember those are going by twos. But negative 4, comma negative 5. Okay, from there we can come up with a slope and make an equation. So linear, yes. Our slope is 10 minus negative 5 over 22 minus negative 4. If you got different points, great. So that is 15 over 26. Again, not clean numbers. I wish I got slopes that were a little bit prettier than this one. Oh, well, I didn't. I wish I did, and I didn't. So if I got it as 15 over 25, that would have been really nice. That would have been 0.6. This is a little less than 0.6, and it's not perfect. So I'm doing what I can. That's why using the calculator later will be best. All right, let's choose a set of points on this line, like 10 and 22. So y minus y1 equals m times x minus 22, x1. Again, I'll leave it exact while I can. Whoops. Y minus 10 equals, so 15 26x minus, now 15 times 22 is 330? 330 over 26. And 330 over 26 is, as a fraction, reduced to 165 over 13. 165 over 13. Now, when I add 10 over, 10 is 130 over 13. So 130 over 13 minus 165 over 13 is negative 35 over 13. So there's an exact equation for my line of fit. Now we're going to use that to plug in 15 for x, get a value out for y, and figure out what's going on. So when x equals 15, we're going to say y equals 15 over 26 times 15 minus 35 over 13. Now I'm going to let my calculator do the rest. So no rounding beforehand. So 225 over 26. 15 times 15 is 225. Minus 35 over 13. So that number is 5.961. So it's around 6. Rounded to the nearest tenth, it's around 6.0. So I'm just going to leave it like that, right? It's around 6. Now, when x is 15 is right there, so is that close to 6? Actually, yes, right? Well, I mean, that's just based off my line being what my line is. So let's interpret that in context. What was this about? Months and hair length. After 15 months, your hair length will be, not how much it'll grow, how much it'll be. Because this is how long the hair is. Your hair length will be about 6 inches. So after 15 months, your hair length, or the person's hair length, whatever, hair length will be about 6 inches. Your hair will be about 6 inches length. That's probably a better way of saying that. Okay. All right. Let's go to number 15. I pray that I make a line that the numbers are so clean, even if it's just, even if they're decimals, as long as it's not a weird repeated, long decimal. I don't want these fraction ones anymore. I want to get one where I make a really good line of fit. All right, hours and battery life. So you're seeing after some hours go by, you lose battery life, that kind of thing, right? So let's see how this one tracks. Is it linear? Who knows? Based on y going up to 86 and such, I'm going to make this one be scaled by 100 and this one scaled by 2s right here because it goes up to 20. So 3 hours of battery life to 3 hours is 86% battery life. So here's 80, here's 90, 86 is going to be about there. The smaller the point, the better, but I'm just not probably roughing it in its right spot. So hopefully that's around 86. 7, 2, 4, 6, 7, 61%, just above 60. Just above 60. I'm trying to make the points smaller as well. So 61. 9, right next to 10, and 50. Okay, that's one of my best points I can plot for you. No real eyeballing there. Actually, I have a best one. 17 and 26. 12, 14, 16, 17. 26, a little bit up from 25 right there. And then 20 and 0. See, now before I do that, right now this doesn't look linear. Right now this looks like there's some sort of curve trend. But the last point is what seems to make it happen here. 20, 0 is what tends to solidify this is more linear because it's now has to bend back down, which means when I make a line of fit, I need to make sure it goes through these points in some sort of way like that, right? Now, is that a best line? Probably not. I'm going to try and work on it. I'm not very good at doing these. It's better when I have a ruler because now I'm just kind of eyeballing what I have here. I have 2 that are above, 3 that are below, but the 3 that are below are closer where the 2 that are above are a little more separated. So maybe that seems like a line of fit. And this time when I drew it, they didn't ever really seem to go through. Let me go one more up there. They didn't really seem to go through any of my actual points, which is fine. They don't have to, right? My goal is to just get something to make a line of fit. Now, I do need to collect 2 data points here. My best eyeballing venture. I'd say this one's pretty good. That's 10 hours and 50% battery life. This is an approximation, by the way, right? Your phone will fluctuate for different reasons. The kind of range it's in, how much you use it, stuff like that. So that fluctuation's there. I don't see any other good points to actually use, which is too bad. So I'm going to have to do my best eyeballing of something else that seems to just work. I don't want to use this right here because that would just be a slope then of like 10 or something. Let's do... Oh, man. Let's pretend like this one here is something like, let's see, I can't tell. That looks about halfway up. Let me move this other point for a second. That looks about halfway up there. So let's do 20, 5. Why not? 20, 5 like that. So with that, first of all, linear. And I'm doing the best I can with this one. At least these numbers should, I think, be cleaner, I think, when we work this out. So the slope, see if I chose something else, it might change it. Slope is, let's say, y2 minus y1 over x2 minus x1. So that's negative 45 over 10, which is negative 4.5. All right. At least this one I have a decimal for, or something that's a lot cleaner. I could also say negative 9 over 2. So negative 4.5. Now my y-intercept, it's going to be close to 95 or 96, but let's figure out what it is based off these two sets of numbers. Let's choose that set of points here, 10 and 50. So y minus 50 equals negative 4.5 times x minus 10. So y minus 50 equals negative 4.5x plus 45. Ah, yes, this is where my 95 comes in. Hey, good, I get some clean numbers. Y equals negative 4.5x plus 95. Now, this is my own line of fit. I don't know if that's perfect for anything or not, but it's pretty good when I'm using what we have to use. So when x equals 15, let's see how that pans out. Now, this is after, so when I'm guessing, I'm eyeballing, it's going to be around, well, the 26 hours or 27 hours that we saw before, just based on the appearance of my line. So when x equals 15, we're going to have y equals negative 4.5 times 15 plus 95. Did I say hours? I should have said percent. So after 15 hours, around 27%. So let's do that. Negative 4.5 times 15 plus 95. 27.5. 27.5. So that interpretation will be, after 15 hours, the battery life will be approximately, I don't know if I said approximately for the last problem, at 27.5%. You will have about that much battery life left. Okay. All right, and then number 16. Shoe size and heart rate. Oh, wow. Now, this is a true one. See, I said correlation doesn't mean causation. The longer time you spend on a phone or whatever, the number of hours that go by, the more your battery life will lessen, assuming we're not charging it, assuming that it's on. This one, so that one sounds like a causation. This one sounds like a true correlation here. Shoe size and heart rate. Just because you have a bigger shoe size does not mean you should have a whatever. Now, there may be a strong correlation. I don't think that necessarily indicates causation, though. Anyway, let's see what this one looks like. I'll scale the... Can we do the thing? Here, let's do the thing here where it kind of does the jagged edge thingy where we're saying we're not starting from true 0. And then let's change the scales there. We can go from, say... Go by tens or something like that. How much do we have to go up to 130? That'd be 50, 85. I don't know. Here, let's just ignore. I'll just call this one as a y-intercept, or as that bottom one. I'll call this one 85. And I'm going to go by fives here. 90, 95, 100, 105, 110. 115, 120, 125, 130, 135. Then I can hit that 132 a little better. So let's see, 90, 95, 100, 105. This probably isn't the best way to do something like this, but 135. At least there I can gauge things a little more approximately. If everything's too packed in within just like right here, that's not very helpful for me. If it's spread out more, that can help me better draw a line of fit. It's all about accuracy. That's for heart rate. Shoe size, I don't have to start at 0 here either, because if I want to get out to 13, let's just do it this way. Let's just say 5, and then call this 10, and call this 15. Like that. Okay, let's try and plot these. So 6 is now here. This I might make a mistake now, but 6, and here's 112. Okay. 8, 6, 7, 8, and 94. 90, here's 94. Oh, this might not be linear. 8.5. See, now I get this one. 8.5 and 100. 10 and 132. Here's that top one. Jeez. And then 13 and 87. 87's right here. Yeah, see, when you look at this data, There's no relationship here. You can draw, listen, there's a line that best fits the data. Maybe it's like that. I don't know what it is. But the correlation is not strong. And I alone was saying, even if there's correlation, it's not going to indicate causation, guys. Having a larger shoe size is not going to indicate higher heart rate or something like that. There may be some links to that, like, oh, because you're whatever. But here, there's truly no correlation. This is not linear. We can't make a prediction. We can't make a prediction about a person with a shoe size of 15 and their heart rate based on what we're seeing here. So we cap it off there. We're done. There's nothing we can say with that. And 15 would also be an extrapolation, which would be really tough to talk about. So we're going to leave it at that. Okay, let's move forward to number 17 and 18, where we model with mathematics. The data pairs X, Y represent the average annual tuition Y in dollars for public colleges in the United States X years after 2005. Use the linear regression feature on a graphing calculator to find an equation of the line of best fit, estimate the average annual tuition in 2020, interpret the slope and y-intercept in the situation. So here we're going to do this. I'm going to go to my graphing calculator. And you'll have to keep these numbers in mind. That's all. You can see the numbers there. I'm going to type those ones in. Okay. So we're going to go to the graphing calculator. I have to move my self now if I want to see the numbers too. Turn it on. And we're going to go to stat and edit. And we're going to type in these X values 0, 1, 2, 3, 4, and 5. And Y values, we're going to type these ones. At 0, we have 11,386, 11,731, 11,848. This is college tuition, years after 2005, on average. For what? For public colleges in the United States. 12,375, 12,804, and 13,297. Uh-oh, this was not 12,804. 12,804. Hope I typed the right numbers. Okay, so from those, couple things. Number one, line of best fit. We go to stat again and calc, and we can hit this linreg ax plus b. Now, when I hit enter on this thing, it's going to do it for L1 and L2. Now, there's a way on the calculator that you can also get the correlation coefficient. I don't think it shows it here. I believe you have to go to turn diagnostics on. I think you have to go to memory. Memory, you have to hit second and the plus. No. Was it catalog? Second 0 catalog. And D, where's D on this thing? A, B, C, D. I have to find diagnostic on. Diagnostic on. Because my calculator resets itself each time that'll happen. So when I do linreg one more time on this thing, I'm going to, there's my R. Okay. So I got R to pop up as well, which shows a strong correlation of these values. Because I can't see the graph right now. It's not linear to me. But here's my equation even still. I got 380 for A. That's basically my M. So I'm going to start writing this equation. So my equation is going to be y equals, I'm just going to write 380, 380x plus, and I have 11,290. I'm just going to round to the nearest dollars for these things there. So that's my equation. 380x. Sorry, I kind of have a typo. Or bad handwriting, basically. So use it to estimate the average annual tuition in 2020, interpret the slope and y-intercept in the situation. So we never drew a graph on this thing. I could show you the graph stuff later if I feel like it's pertinent for what we're doing or if they require us to do it. But that's my equation for the situation. Now let's interpret this first before we estimate the other thing. We're interpreting, so for the y-intercept, first of all, is saying in year 0. In the year 2005, the average, did they say average for this? Average annual tuition is approximately 11,000. Where's dollar sign? That's percent. $11,290. That's the y-intercept. The slope interpretation is every year the average annual tuition increases about, oh, I didn't write the word tuition. Increases about $380. So that's the interpretation of those two things based off the line of best fit. Now your calculator knows how to do the line of best fit. It's doing it based on getting the correlation coefficient the highest it possibly can be. And you can tell there was a strong correlation in these numbers here. It said 0.986. That is a very strong correlation. It shows that as the years pass, it seems that college tuition is indeed increasing. Okay, so now they did say estimate the average annual tuition in 2020. Now the year 2020 is 15 years after 2005. So we're going to say when x equals 15 in 2020. So we're going to say y equals 380 times 15 plus 1290, etc. Now here's where I'm a little wishy-washy on my stuff, because I did write rounded values. I did write rounded values. But what I want to do is actually use, do I want to use the actual numbers? I mean, these are also decimal values themselves, but I have to type these numbers into my equation thing, in my equation finder, or I can obviously plug it in. So I can do 380 times 15, etc., plus 11290. But also, you know, I'm curious to use the one, because there's that actual number. I'm curious to use this number as well. I want to see how much this changes. It'll change by a couple dollars at least. So times 15, and then plus 11290. Now this one rounded won't matter as much. That 09 is just going to be an extra 9 cents added, but I'm just going to put it in anyway. So if I type in those numbers exactly, the difference is 52 cents. Okay, so it's just cents on the dollar. I guess I'm going to use the rounded numbers then, as long as I feel like I rounded my numbers best anyway. So, okay, not increasing by 52 cents. So in 2020, I'm expecting it to be $16,990. So 16,990. Let me do that again. And I already stated in 2020. So that's the expected value there. Now, they said you could also use the calculator to graph this. This is going to take a lot more time if I do that, though. I could do y equals 380x. I'll show you on this one, and then say, unless they want us to graph it later, I'm probably not going to do this. But if I do that, and go to my graph thing right now, and you can see nothing, because it's out of my window range. You'd need to know something about this window range, such as where it starts, and how much it goes to, and what you want your window range to be. I can make my x be 0 here. That's the year 2005. And I can go to about 20 years later if you want to. So we can make sure 15 is in the range. The y, I want to start at a low, maybe $10,000. Let's go to a high of maybe, I don't know, 20,000. We know it goes to 16,000 eventually. So it's going to go beyond that. This will at least show me my line. There's my line of fit. Now, it doesn't show my points. If you want to get your points from here onto there, you have to go to stat plot, which is above y equals. You have to hit second and y equals and turn stat plot on for whichever points you're trying to do. From L1 to L2, for example, I have to turn that on, and it shows the kind of data points you want. So when I go to graph now, those will be my points right there. Oh, I don't need that many years. What did I do for my... Oh, they did the first 5 years, right? So 15 years is way out here. So if you want to find out what it is on that one, you hit the button trace, and you type in an X value for yourself. Whoopsie. I don't know how to... Wait, you trace, and then you scroll on this thing, I should say, until you... They said use trace. I don't remember... Maybe value. They said trace. I like to use... There it is. All right, you go to value, you go to second, and you hit calc, which is above trace, and you go to value, and you type in your number. So when I type in 15, I get that value right there, which is the 16990. So it shows what that is. It shows this is a pretty good line of fit as far as what they did. I mean, it should be the line of best fit. But yeah, there it is. All right, that's number 17. Let's jump to number 18. So I won't do a graph unless I feel I need to, or unless they ask me to here on out. So number 18, the table shows the number of tickets sold for a concert when different prices are charged. Write an equation of a line of fit for the data. Does it seem reasonable to use your model to predict the number of tickets sold when the ticket price is $85? Explain. So they didn't say use the linear regression feature for it. So I'm not going to do that this time. This time line of fit sounds like it's on me. So table shows number of tickets sold. Write an equation for the line of fit of the data. Does it seem reasonable for your model to do it here? Oh, pretty interesting. So they're asking for, does this extrapolation seem nice? And by the way, this one was very much an extrapolation. We had for years 0 to, what was it? I mean, this had 0 on it. But we had years 0 to 5 for number 17. So we had to talk about 15 years out. That was a true extrapolation. So will this one. So for this one, I'm going to do the same things I did last time. I'm going to use my graph axes, but I am also going to change the window range for this because I have to be in the hundreds here. I have to go from 395 to 450. I'll make this will look really bizarre for us, but this is just about accuracy. I want this to be up here to 450, and I'll make this one 395. I think that'll work out because I think this will now be 400, and every 5 will be, or every increment will be another 5, so 425 like that. So 410, 405, 410, 415, 420, 425, etc. 430, 435, 440, 445, 450. Okay, so those are some points there. And here, I go from 17 to 26. I think on X, I can make this 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I'll make this one 26. And 21, this is not going to look pretty at all. So 16 will be right there, so I'm not going to use that one. So at 17, so this is 17. At 17, I'm going to have 450. My goal is to just get the line. My goal is to get the line, and as far spaced out as I can, I'm going to use. At 20, 18, 19, 20, I'm going to have 423. Okay, at 22, 21, 22, I'm going to have 400. And at 26, I'm going to have 395. So let me erase the 26 that's there because I got to plot it right there. 26, I'm going to have 395. Boom. Okay, does it seem reasonable to, let's see, write an equation of a line of fit for the data? Does it seem reasonable to use your model to predict number of tickets? No. So if you see here, I look at the points that I have. I'll make them a different color. So I have this point here, 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 and here. What you see here, what you see here is more of an upward trend. This thing seems to be curving itself out more over time. A line doesn't seem to work best for that. I'll make a line, they want me to, but it doesn't seem to work to predict something far out. Maybe within, sure. But a curve would probably still be better. But here, doing a line, you'd want to do some points above, some points below, stuff like that. And maybe it's something like this, right? Okay, that could be my line like that. I want to make something that seems to go through some points, though. So that one doesn't really. Let's see. Probably go downward more like that. I'm trying to see what would best. There's no real line of best fit here. That's the problem. And I'm no good at this either. That's the other problem. Okay, I'm going to makeshift it so the points seem decent. So I'm going to say like, okay, that looks pretty good. And I don't know if it is or not. I'm going to say that looks pretty good. And if that looks pretty good, I want to do 2 points as far out as possible. So this one right here, I think that was 26, right? 26 and 390. And this guy here seems to be hitting right at the top, which is 16 and 450. And I know those aren't the exact data points that we have. This is to make your line of fit, right? At least this one will give me a clean number. That's really all I'm going for. So my slope is going to be, the thing is, though, this shouldn't work in general. 390 minus 450 over 26 minus 16. That is negative 60 over 10, which is negative 6. So there's that. The y-intercept, is not 450. The y-intercept, we have to do, choose a set of points, so 16 and 450, sure. We'll do y minus 450 equals negative 6 times x minus 16. And that's y minus 450 equals negative 6x plus, is that 96? I think 96. Add 450, you get y equals negative 6x plus 546. Okay, there's my line. Does it seem reasonable to use your model to predict the number of tickets sold when the ticket price is $85? Well, I'm going to say no just off the fact that this thing seems to curve outward. That thing seems to curve outward. It seems to kind of be sloping itself off. So as you increase the ticket price, you seem to be selling. The number of tickets sold seems to be kind of plateauing a little bit. You're still going to be selling that same amount. That also doesn't seem reasonable. But let's see what happens when you substitute 85 into here. when x equals 85, what happens? We get y equals negative 6 times 85 plus 546. Maybe it is reasonable. I don't know. I felt like this didn't seem like a good model, but maybe it is. Y is about negative, whoops, I'm still in that other screen. Negative 6 times 85 plus 546. Oh, I have a syntax error. What did I do? There's a random one there. Okay. I have 36. Y equals 36. Now, it said, does it seem reasonable to use your model to predict number of tickets sold? I said no before because I said this didn't seem very linear. You know what? It's not that it doesn't seem linear. It's that the sample size, it's that I feel like from these four, I can just draw a curve out. My concern for this thing was it was going to be plateauing out this way, but maybe it's just not enough data points. The next concern was going to be when I calculated this, I would get a negative number. But now that I think about it, having less people for a higher ticket price seems like it could be reasonable. It's not a negative value. This seems plausible. Maybe I was a little too harsh about the correlation being weak. It seems plausible, given that there are less tickets sold, significantly less tickets sold, for a significantly higher price, higher ticket price, and the number of tickets sold is still positive. Okay, I apologize for poo-pooing on the problem before. I feel like with the 4 data points, it had more of a curve. But you know what? Once you get a 5th data point, and that's what I said about the other problem. Once you get a 5th data point, let's say like right here, suddenly things look pretty good. So, you know, I kind of just wanted more. I just wanted a larger sample size. I wanted more data. Seems okay. I don't know, based on what I have. Maybe my line isn't good, though. Depends. All right. In exercises 19 to 24, use the linear regression feature on a graphing calculator to find an equation in the line of best fit for the data. Find and interpret the correlation coefficient. Okay. We're not drawing the line. The calculator will for us. Boom. But that would be the idea of the line, right? But this time we got to plug in these points, which means we got to know what the points are. So I'm going to write out over here what the points are, and then I'm going to type them in. So we have 1, 1, 2, 3, 3, 2. I don't want to mess up here. 4, 3, 4, 5. There's no context for these, by the way, so we're not interpreting the data in context. We're just interpreting the correlation coefficient. Is it weak? Is it strong? Things like that. I'd say this one is moderate. I see a bit of a trend. It's not much of a trend. It's probably going to be around 0.7 or less. Or maybe I'm wrong. Maybe it's higher than I think. But 6, 4. Okay. These are the points I'm going to plot. These X's, these Y's, or I could make a table out of it. I'm literally going to make a table, but I could write it as a table as well if that's preferred. So I'm going to go to the graphing calculator. I'm going to go to this list right here. You want to clear these lists. Go to the top, hit the clear button, and go down. It'll clear out. Go to the top, hit the clear button. It'll clear out like that. So I'm going to type in the numbers for X. 1, 2, 3, 4, 4, 6, 6. And over here I'm going to type, and they have to associate 1, 3, 2, 3, 5, 3, 4. Okay, so from there, now first of all, let me default this window range in case I want to show the points here. And let me clear out this equation. Okay, if you want to see the points on the graph, here they are. Okay, if you want to see the linear regression, we'll go to Stat, Calc, and LinReg. This is where we can come up with the equation. They say, at least the numbers are clean, find an equation of the line. Because the decimals are exact here, I'm going to write that as y equals 0.42x plus 1.44. If you'd like to see it as an equation, or on a graph, 0.42x plus 1.44. And I'm going to close in on the window range the same as the thing has on here. I'm going to go from 0 to 7. This is on the problem itself. And I'm going to go 0 to 6 on y. Okay, so here's what this will look like. There, T-H-E-R-E, is their, T-H-E-I-R, line of best fit for that thing. Now, the correlation coefficient they have is, like I said, less than 0.7. 0.6148. R is about 0.6148. Okay, so I wrote out some of the stuff. I came up with the number. Find and interpret the correlation coefficient. There's the correlation coefficient. Interpreting it talks about what's the strength. Now, and is it positive or negative? First of all, it's positive. There is some, it's kind of weak, positive correlation of the data. You also saw the R squared, the 0.378, which means around 37.8% of the data can be explained by relating X and Y. Anyway, there's some positive correlation of the data. Not very much. Not super weak, but really not saying there's a correlation. Number 20, or a strong, moderate correlation. Number 20 looks a lot stronger as far as a correlation goes. Let's copy down the data points here. I got 1, 2, 1, 3, 2, 3, 2, 4. It's kind of a step function. I could probably predict what the next sets of points are. 3, 4, 3, 5, and 4, 5. Regardless, it seems to have a pretty strong one here. You're going to see something significantly higher, maybe even in the 0.9s, and also positive. So let's go back to the graphing calculator, do the same thing. I'm probably not going to do them on graphs anymore. I just wanted to show you what that one would look like. So clear these data points out. Okay. We got 1, 1, 2, 2, 3, 3, 4, and 2, 3, 3, 4, 4, 5, 5. Okay. Let's do linear regression for this one. This equation, ooh, this one's now more rounded. But all right, 0.88 is the number. So y equals, I'm going to say 0.88x plus 1.69. It's about as close as I can get for the numbers there. And R is about 0.8846. That's pretty strong. Again, you get around 0.9. You get 0.9 or higher, you're saying strong. So this is a pretty strong. This is a pretty strong positive correlation. And it's positive, meaning the slope of this thing would be positive if you draw that line through there. Or there is a pretty strong positive correlation between X and Y. All right, number 21. Now 21, I'm seeing more of a downward trend. Not a very strong one. Strong-esque, maybe around the 0.7 range, but I'm seeing more of a downward trend. If you want to draw it through the line points, it's probably something like that. It's okay. It's probably 0.7, 0.75, something like that. It's pretty good. But it looks negative this time. So when you see the slope, it's going to be negative. The R value is going to be negative. Negative doesn't mean bad. It just, once again, means something where you are going downward. X and Y relate in a downward trend. As X increases, Y decreases. So number 21, I have 1, 4, 2, 3, 3, 4, 3, 2. Don't miss any points. 4, 3, 4, 2, and 5, 2. I hope I did those right. You might be wondering how to calculate this stuff on your own. You can find a formula online, and it's not fun. It's not pretty. It takes a long time. It's not just a one-trick pony kind of formula. You're trying to find the distance between. It's weird. It's really weird. Even calculating the R value and stuff, really, really weird. So doing this on your own, accurately to how the calculator does it. Anyway, 1, 2, 3, 3, 4, 4, 5, and 4, 3, 4, 2, 3, 2, 2. Okay, here we go. For this one, so y equals, I'm around to the nearest hundredth, negative 0.45x plus, and b value 4.26. Now the R value, oh, it's weaker than I thought. I said it was around 0.7, so, or negative 0.7. So R is negative 0.6689 when rounded. Okay, so it's okay. I mean, you know, it's more than this one, the 0.61. This gets to be okay. There's a moderate negative correlation. It's moderate. It's almost there. Once I see 0.7 or higher, I say there's a correlation. 0.75, it's like, all right, your data's starting to relate. Yeah, 0.7, 0.75 is where you start to say there's a correlation. Number 22 is going to be pretty strong. 22 is going to be the strongest of the bunch, it looks like. It will be negative, but it looks to be strong. All right, our points are 1, 5, 2, 4, 2, 3. 3, 3, 3, 2, 4, 1, 5, 1. I'm predicting, wait, what was number 20? 0.8. I'm predicting something in the negative 0.9s this time. It's my prediction. Okay, let's see. Let's go to this and clear out the numbers. Okay. 1, 2, 2, 3, 3, 4, 5. And 5, 4, 3, 3, 2, 1, 1. Okay. Let's check her out. We have, all right, negative 0.93. So this equation, y equals negative 1.04. How about x plus 5.68? And r is about negative 0.9347. Okay, so that's going to be a strong negative correlation. I agree. I think those points seem to go pretty well with a downward trend. There is a strong negative correlation. Okay. All right, numbers 23 and 24. 23 should also be strong. Probably just as strong. I'm guessing something above 0.9 again. So 23... but this time positive, right? So we have 1, 1, 2, 1, 3, 2, 4, 2, 4, 3, 5, 3, and 6, 4. Okay. Let's go back to the calculator. Stat edit. At some point, you're going to learn the stat edit thing pretty well, but obviously we don't do this isn't a statistics class, so at some point we stop doing it as well. But in reviews and stuff, we want to know what to do. 1, 1. Whoops, not 1 again. 2, 2, 3, 3, 4. Okay. Ah, no. Quit. All right. Yeah, still a high correlation, even higher. So y equals 0.61. X, I thought all these numbers would be perfect, plus 0. Let's say 0.97. I want to get that extra little bit in there. Let's even add 0.613x. So I added a little bit more. I wanted to get a little more precise. Now R is about, I cleared away, but 0.9465. 0.9465. You're looking strong, my friends. There's a strong positive correlation. All right. And number 24. How long have we gone? Hour 40 about. Jeez. I was hoping with lesser questions. Number 24 is going to look pretty strong. I'm guessing the 0.8s, negative 0.8s. All right, number 24. I got 0.4, 1.4, 2.3, 3.3, 3.2, 4.2, 5.2. It seems to be spreading out more though. Probably the 0.83. I don't know. I don't know if I'm really good at that. I'm just saying it's pretty strong. Okay. For the marbles. Oh, negative 0.9. It's stronger than I thought. I just thought when it was spreading out, it's going to spread out even more, but it can't see those other numbers. So, okay. So, y. So, I'm going to say strong again. Negative 0.48 x plus 4.08. Interesting equation. And then r is negative 0.9087. are negative 0.9087. All right, still strong and negative. So there is a strong negative correlation. I'll say pretty strong. Yeah, there is a strong negative correlation. Not very strong, almost pretty strong. If it was in the 0.8s, I'd probably say pretty strong. Okay, guys, that is those ones. When it says interpret, that's how I'm interpreting. All right, number 25, open-ended. Give two real-life quantities that have a positive correlation, a negative correlation, and approximately no correlation. Explain. Two for each. One of the big ones that you'd probably say, see, I don't want to say something that I won't know anything about for the no correlation. Positive correlation, you know, one of the big ones that we want to say is like smoking and lung cancer. Now, correlation doesn't always mean causation. Smoking doesn't always lead to lung cancer, whatever. But there's a high correlation between the two things, right? That as let's see how to write this. Bullet point maybe. As an individual smokes more packs a day, their likelihood of lung cancer raises. Now, that's not necessarily causation. You have to remember, when I say that, I'm not saying it causes it. I'm saying that if you look at data for something like that, there's a likelihood that you'll see something with that. I'm trying to see how to best format this. This is just a logistical typing thing. I'll just write it like that. All right, so there's one. Let's do another one with studying and grade, exam grade. Now, these are positive ones. As an individual, let's see, the more you study, the more hours you study, the higher grade percentage you'll obtain. Now, again, correlation doesn't necessarily mean causation. When it talks about the link of these things, what you need to keep in mind is this, especially the studying one. Someone who studies more, they might not get a higher exam grade because they studied more, but someone who studies more is likely more studious. More studious. They're just a more intelligent being. They understand studying is a way to go about things, and even if they didn't study, maybe they'll still pass just because they're a studious person. But the point is, they might just be studious in that way, right? Maybe their parents force them to do more studying, and then they also have a higher expectation of grade as a result of something. So it doesn't necessarily mean one causes the other, and I want to keep stating that over and over when we do them. All right, let's do negative correlation. Negative correlation. So as something increases, something else decreases is basically what you'd say here. And I want to try and do something that the book didn't already do. So I might have to pause and think about some things. It should be pretty easy to do, but let's say the weight loss, exercise and weight loss. And weight. The amount of time exercising the amount of time you exercise, the more weight you lose. Once again, a lot of things can do this. Maybe you are an exercise hound and fiend and whatever, which means you're also just a health nut, and maybe you just eat more healthily and stuff like, like there are a lot of different things that can also make this thing be what it is. But being a negative correlation, again, doesn't mean bad. In fact, this can mean good. So you exercise more. So not the amount of time, the more time you exercise. The more time you exercise. Okay, let's do another one. Let's do, I don't want to do a time one. They already did a dollar amount set in sales for ticket things. Let's do let's do game time. Let's see. Game time versus attendance. the longer a game goes on, the smaller the attendance gets, the attendance gets. You know, if a game goes deeper into extra innings, more people start to leave. I don't know, something like that. I don't know. I'm just thinking of that. Okay. There is a no. We have to do one for no correlation as well. This one's just kind of hard to do just because you just have to find two things that just do not link at all, and it's just kind of weird to try and be creative with that or whatever. It's probably really easy, but I want to say, and there are some where people can argue that it still works, but just do totally unrelated things, right? That doesn't mean there isn't necessarily a relationship, though. See, that's the thing. They might still have a link, like, let's do totally two unrelated things. Let's do divorce rate versus margarine consumption. There shouldn't necessarily be a link. There isn't necessarily any link between the amount of margarine you consume and the divorce rate of individuals. Maybe there is. I haven't looked at it. I have no idea. That's what I'm saying. This is what kind of makes this one hard, because I don't know if there's a link or not. Let me kind of minimize these a little bit. So okay. Last one. Let's do, what's another just random link? I'm at the bottom of my own page. I want to do something with Taylor Swift. I don't know what. I have no idea. This is a stupid amount of time. I'm gonna pause and think about one. Okay, let's do number of. I'm a sport nut, so number of fantasy sports leagues that you have. Number of fantasy leagues versus fingernail length. Enough said. Literally. If you have this many, I mean, you can do anything. Number of cars owned. How about this? If you don't know what fantasy leagues are, number of cars owned versus fingernail length. Number of kids owned. I guess you don't own kids. Number of kids that you have versus fingernail length. Right? So that stuff is not, there's nothing to speak on with that stuff. Maybe there's a correlation. I don't know. But those are just the explanations I have. All right. Let's keep moving forward. All right, number 26. How do you see it? You secure an interest-free loan to purchase a boat. You agree to make equal monthly payments for the next 2 years. The graph shows the amount of money you still owe. What is the slope of the line? What does the slope represent? So, looks like a down 1 over 1 thing, but it's not actually 1. This is down 5 over 4. Down 5 over 4. So on part A, the slope is negative 5 over 4, which is also negative 1.25. So I'm trying to see which one is better to state right now. Dollars. This is hundreds of dollars, by the way. That's hundreds of dollars. So negative 1.25 $100 is negative $125 $100. So let me do that one. So every month, every 1 month, your loan balance decreases $125. So this is kind of interesting on as far as the how do you see it. It's an easy kind of answer to start off with. The interpretation's a little weird. Because not only is the scale here, but this is in hundreds. So negative 1.25 hundred is negative 125. So that is the interpretation of part A. Part B. What is the domain and range of the function? What does each represent? The domain, this doesn't have an arrow going to the left side. We start at month 0, but it seems to go on after that. So the domain is x is greater than or equal to 0, and the range is, let me do it up here. Whoa. x is greater than or equal to 0, and the range is y is less than or equal to 30. Now it seems based on the arrow it keeps going downward, which means it does something like that. It says, what does each represent? This represents the time in months, and this represents the loan balance in hundreds of dollars. I'll say 100s in 100s. Okay, so now I thought it probably would have stopped at this point, but there is an arrow, so it does seem to keep going beyond that point. I would have thought after 24 months you've paid your debt or whatever. Okay. Part C, how much do you still owe after making payments for 12 months? So here's 4, 8, 12, and we go up to this guy right here. How much do you still owe is going to be this number, which is 15. Remember, that's not $15, that's $1,500. So based off the point that is 12, 15, that does state you still owe $1,500 after 12 months. After making payments for 12 months, you still owe. Okay, that's part C. Okay, let's keep moving forward. Number 27. Making an argument. A set of data pairs has a correlation coefficient of R equals 0.3. That's very low. Your friend says because the correlation coefficient is positive, it's logical to use the line of best fit to make predictions. Is your friend correct? Explain your reasoning. Your friend's not correct. Positive, my friend is not correct for two reasons. One doesn't lead to the other here. For one, a positive versus negative, a positive correlation is no better than a negative correlation when it comes to use of line of best fit. And the other problem is, let's see, for another, R equals 0.3 is a weak correlation. It's very weak. It's a weak correlation. Period. You should not. Please, you should not use. Friend. All right, number 27. All right, number 28, thought-provoking. Points A and B lie on the line y equals negative x plus 4. Choose coordinates for points A, B, and C, where point C is the same distance from point A as it is from point B. Write equations for the lines connecting points A and C and points B and C. Is C on the line as well? I don't know if I read this right. I'm trying to copy paste a graph. Give me a second. There we go. I guess it wouldn't make sense. If C was on the line, it would be the same equation, y equals negative x plus 4. But 28, so this is kind of open-ended, right? That's what thought-provoking generally is, negative x plus 4. So that line, first of all, looks like this. It's the slope of negative 1, and it goes through here. So I can choose any point on here, especially one of these ones, for points A and B, and then I got to choose C somewhere off of that. Now, I can be fancy with it, or I can make it very easy. It depends on what I want to do. It's my choice, and this is open-ended. It's also your choice as well, but you just need to make sense of what it is that you're doing. So there's y equals negative x plus 4. Let's choose points A and B. I'll choose A right here, okay? And I'll choose B right here. Let's choose C somewhere random. C will be right there. Okay, A, B, and C. Now I need to make the lines that go through AC and BC, right? That's the idea. So I'll make them a different color. Here's AC. I don't know. I'm just making up random colors for this. And here's BC. Okay. Now, what are those lines? What are the equations of the lines? It's all based off the points. So A is at the point negative 2, 6. B is at the point 8, negative 4. And C is at the point 5, 8. Okay. So for the two different lines, we need to find their slopes. I need to find the slope of line AC. Slope of line AC, which is from A to C, 8 minus 6. Listen, I can count these ones, rise and run. I can count this as up 2 over 1, 2, 3, 4, 5, 6, 7. 2 sevenths, 2 sevenths. And the slope of BC, line BC, is going to be down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Down 12 and right 1, 2, 3. So that's negative 12 thirds, which is negative 4. Now, these are two different lines and two different things here, and we can use any point for this. I'm going to go ahead and use C's point of 5, 8 for both of them on point slope form. It says write equations for the lines connecting them. Okay, I just want to make sure that's all we're doing. So I'm just going to keep it in point slope form. So for AC, for line AC, it's going to be y minus, and my y1 is going to be 8, equals m times x minus x1 right there. And I'm just going to leave it like that. They're not going to get any deeper in slope-intercept form if I don't have to. They didn't say to. And BC is going to be y minus 8 equals negative 4 times x minus 5. You could get deeper into it, make it the slope-intercept form, but we're good. This is just a very open-ended thing. I just played with whatever. All right, number 29. Abstract reasoning. If x and y have a positive correlation and y and z have a negative correlation, then what can you conclude about the correlation between x and z? Explain. Well, let me start with the explanation here, because maybe I can make sense of it. I think I have an answer in mind. But if x and y have a positive correlation, x and y, that means as x goes up, as x increases, y increases, just as a general thing. If y and z have a negative correlation, right, have a negative correlation, that means as y increases, z increases. So what's our transitivity thing that we can do here that makes most sense to us? As x increases, y increases, z decreases, I should say, decreases. So that would mean as x increases, so the relationship, so as x increases, z should decrease. Decreases. This means that x and z should have a negative correlation. And that's the answer I'm going with there. My explanation was everything that led up to that. Okay, cool. Number 30. 3 more questions. Mathematical connections. Which equation has a graph that is a line passing through the point 8, negative 5 and is perpendicular to the graph of y equals negative 4x plus 1? This is something you would have done in IM1 for sure. So if I have the line y equals negative 4x plus 1, and wait, perpendicular, let me say that again. Perpendicular to y equals negative 4x plus 1, and it goes through 8, negative 5. What you want to first do is say the slope of this line is negative 4, so the opposite reciprocal slope, perpendicular, this is negative 4 over 1, so this is positive 1 over 4. So automatically, that means this answers out, and this answers out. It's either A or D. Now what I'm going to do is substitute this into my, as they've been doing, point slope form. We'll say y minus y1, so plus 5, is m times x minus 8. We'll distribute the 1/4 into that. We'll get 1/4 x minus 2, and we'll subtract 5 over, and we get 1/4 x minus 7. So that should be the answer. 1/4 x minus 7 is D. So that answer is D right there. A is out. Okay, number 31, problem solving. You are participating in an orienteering competition. I have no idea what that is. The diagram shows the position of a river that cuts through the woods. Okay? You are currently 2 miles east and 1 mile north, I guess right here. 2 miles east and 1 mile north of your starting point, the origin. Yep. What is the shortest distance you must travel to reach the river? Okay, so closest distance from a point to a line is the perpendicular distance. So I want to find the one that goes like perpendicularly to it right there, and then I'll kind of find the thing. They say what's the shortest distance? So I got to find that perpendicularish part there. So basically, I got to come up with the equation of the line that passes through this perpendicularly. So I need to, just like the last one, I don't know where this perpendicular stuff came from. Perpendicular to y equals 3x plus 2 through the point 2, 1. So we'll do the same thing as before. I got a slope of 3. I need to get the opposite reciprocal slope, which is negative 1/3. And I need to do it through that point. So y minus 1 equals negative 1/3 times x minus 2. So this is a fraction basis. This is negative 1/3 x plus 2/3. And I got to add 1 over. 1 is 3/3, and 3/3 plus 2/3 is 5/3. So here is the equation of that line here. I need to find the distance. Oh, now I need to find, okay, so there are two more things I still need to do, unless I'm misinterpreting this. Now I need to find the point where this line intersects with this line. So when do these lines, what is the xy, for, what's the system of equations? What's the solution to the system of equations for this? And then I need to find the distance from 2, 1 to that point. I need to find the distance from 2, 1 to that point. So there's a lot of things I think we got to do here still. So I got to set 3x plus 2 equal to negative 1/3 x plus 5/3. Find the x value that goes here and the y value that goes here. If I multiply everything by 3, that'll help me clear out this fraction stuff. So times 3 here, and I'm going to get 9x plus 6 equals negative 1x plus 5. The 3's cancel. I add x to both sides, and I get 10x. I subtract 6 to both sides, I get negative 1, so x is negative 1/10. Apparently, that's where they should intersect there. Oh, you know what I noticed? Hold on. This doesn't change my answer, but my 2, 1 is actually right here. Notice how these go by 0.5, etc. That shouldn't change anything. I'm doing everything algebraically. So this won't look perpendicular anymore, but technically I guess that's how it works. Because it doesn't look perpendicular anymore, because this goes by 0.5s and this goes by 1s. That's kind of weird. Anyway, so x is negative 1/10. The y value when x is negative 1/10 is, let's plug it into the 3x plus 2 one. 3 times negative 1/10 plus 2, which is negative 3/10 plus 2. 2 is 20/10, which is 17/10, or 1.7, either or. But that xy is negative 1/10, 17/10. I think at this point, I want to use decimals, so negative 0.1 and 1.7 as the numbers. Now I need to find the distance between, what do they ask for? The shortest distance? Distance between that point, negative 0.1, 1.7, and 2, 1. So that's the Pythagorean theorem usage distance formula, however you want to put it. So the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared, which is the square root of 2.1 squared plus negative 0.7 squared. I think that's 4.41. 4.41 plus 0.49. Oh, is this exact? Oh, sort of. Oh, which is square root of 4.9. Is that 0.7? Oh, I guess it's not 0.7. I guess it's a random number then. So square root of 0.49. I was hoping it would be whatever. Square root of 4.9 is 2.213. It's around 2.214 miles. All right. I don't know if there's something that I screwed up from one part to another. I feel like all that stuff did go into play, and there's a lot with that one. I feel like that should be one of those critical thinking problems, but it's one of those ones where, I mean, we went from one thing to the next. I can relay everything back if you'd like me to. So let's go back to the beginning and see what exactly I was doing here. So first of all, for this problem, give me 1 second here before I move forward. All right, so first of all, for this problem here, shortest distance is perpendicular you want to draw a perpendicular line that's going to get your shortest distance there. So I need to find out the distance between my point that I'm at and the point that it goes to. But to find the point that it goes to, I need to get the equation of the line, find out where it intersects with the other line. That was the negative 0.1 comma 1.7 value. The distance between uses distance formula. So that was my whole idea behind everything that I was trying to do with that. And then the answer is in miles. So with all that said, we got to that number, which was 2.214 miles about. So quite a bit of work to get there, but I think we still got there. Okay, last question is number 32. Past the 2 hour mark, but here we go. Number 32. Data from North American countries show a positive correlation between the number of personal computers per capita and the average life expectancy in the country. Does a positive correlation make sense in this situation? Explain. Yeah, so, well, first of all, a positive correlation would state that, so a positive correlation, let's make sense of it first, would state that the more personal computers per capita, the higher average life expectancy. Does that make sense? It does to me. The idea here, well, there are two ways I can go about it. I'm thinking of one more versus the other. When I'm thinking personal computers, I can think one in terms of like they can research things more and whatever, but that doesn't have to do with personal computers. Personal computers to me are a luxury item. They're not essential. They're a luxury item, something you can afford. Higher life expectancy might be somewhere that you can afford something more. Maybe you have a good secure job and, like whatever, you just like that. So a positive correlation makes sense because personal computer owners also may be wealthier. And there's likely a positive link. And there is a strong link between wealth and high life expectancy as far as age. I'm not going to explain that one. I think for us we can kind of make sense of that one there. Okay, part B. Is it reasonable to conclude that giving residents of a country personal computers will lengthen their lives? Explain. No. Again, correlation doesn't mean causation. What I'm doing is I found another link within there that was the wealth aspect. Now that you give them personal computers, unless now, I can research more things about wealth. No. No. Correlation doesn't necessarily mean causation. There could be other links in the chain, such as wealth, that explain both the personal computer ownage and, I guess it's not really a word, and average life expectancy. Once again, so just because you give them more computers, you're like, hey, here's a computer, that doesn't make them wealthier, right? That doesn't change different things about their needs and their, like, whatever that would do things life expectancy. So no, not unless you think it means causation and that having the computer itself will do something to give you more life expectancy. Like I said, you can research more things. You can do that anywhere. You can do that at a library. All right, guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching here. I don't know if there was something that I struggled with talking about during the lecture or anything, so apologies if I did. Ooh, that guy looks scary. And yeah, so this one seemed to be a good link in the chain when it came to talking about transformations of things. Although it was kind of random, it seemed to be kind of some IM1 basis, although some of the questions got a little heavier. Hopefully you had a graphing calculator to follow along with me. If not, hopefully I did the rest of the stuff for you. You could use other graphing calculators online like Desmos or something like that to get some of those links, but you have to know how that stuff works, and I wasn't here talking about it. But if you have more questions for me, ask it in the comment section down below. So thank you. Take care. I'll see you in the next one.